So the task that I was given for this first piece of this is what is actually happening to the tendon. So what is, when we actually load it with heavy weight, what is the impact to the connective tissue? And then what is its adaptation? So when we talk about using strength training to improve tissue quality, to develop all the systems of the body, what is actually developing by how much and how? So we're going to start, everyone here should be familiar with this, I won't spend long. Tendons connect muscle to bone, transfers muscular force to the system of levers. It doesn't really matter if your muscle contracts if there's not something to connect that muscle to the bone to move that system. Ligaments connects bone to bone. Those are incredible gross oversimplifications, because when you look at abitendinosis, when you look at a bunch of different setups, you can end up with anywhere kind of on a myriad of those two connections. But let's just assume ligaments connect bone to bone. Because there is no active tension, you do not actively control by muscular contraction where a ligament sits or where a ligament extends to. Because of that, a ligament is, as Doc Sully said, it's a little less dynamic in that context, and it really just serves as a delimiting tissue. When you look at, where did that happen? Really serves as a delimiting tissue. So if you find in the back, for instance, the intervertebral ligaments getting into a position outside of their boundary, that's when you start looking at ligamentous damage, but you're not actually trying to control their position directly. And then cartilage protects and lubricates the joint surface, like Sully talked about. A couple of things we're going to look at here. Most of the research done on tendons in particular are done on the Achilles or the tendons of the knee. The Achilles, because it's the largest tendon and is the easiest to measure in animal models. When we look at the Achilles, connects the gastroc and the soleus, they all kind of combine into the Achilles tendon, connecting it to the calcaneus. So when you see in the research also the calcaneal tendon, causing what we would classically call a calf raise or a heel raise, but plantar flexion of the foot. And when you look in the research, there's kind of there's a disjointed nomenclature for the tissue of the knee. You have the quadriceps tendon. As it comes over the patella, there's a few interactions with the patella itself, but also the fibers of the quadriceps tendon at top continue down into the patellar ligament, which connected the tibial tuberosity, causing knee extension. We all know that. When you look through the literature, you'll see patellar tendon and patellar ligament being used to describe differently, depending on where they are actually taking measurements from, above or below the knee. You will see them trying to make the distinction, the quadriceps tendon and the patellar tendon, which is an incorrect nomenclature for what's coming off the patella down into the knee, or the tibial tuberosity. And then you will see that split, the patellar tendon, the patellar ligament, describing two completely different tissues. You see even here in Gray's Anatomy where this is pulled, back then called the quadriceps tendon in the patellar ligament. So sometimes as we get into nomenclature in some of the literature, you can see little bits of split that we have to clarify. When we look at tendons and the purpose of tendons, often we think of the big muscles, we think of the ones that we work with all the time. But when we look at their qualities and their structure, we have to remember that tendons control not only every muscle's interaction with bone, but they can operate in unique ways. When you look here, this is obviously cut away of the flexors of the arm. They all kind of meet up at the common flexor tendon, and you see how the body of the mass here in the upper arm is controlling in many ways the movement of the fingers, the extension of the wrists and hands, because it would be infeasible, it wouldn't work to have that body of muscle all the way down by the wrist, which has to have that kind of mobility. So all of a sudden, when we start thinking of tendon hypertrophy, increase in tendon size or increase in cartilage size, we have to ask ourselves, where is that an optimal adaptation for it to hypertrophy, or is it optimal for the tendon when we look at strain and the reasons why we might want to increase stiffness? Well, why wouldn't the body evolve or adapt over years to bring the tendon smaller and the muscle closer to the action, essentially? But when you look at the hand and the puppetry of the hand, oftentimes having these long, slender, vulnerable tendons or different arrangements which do not inherently make sense when we look at it from a vulnerability perspective actually create the effective movement that we know works for us as Homo sapien. Now, looking at ligaments, the ACL and the PCL take the massive bulk of interest in the literature. For obvious reasons, for sports injury, they're incredibly prevalent, and they're very interesting and useful to us as models for injury and models for structural damage. So when you look at these two, I just highlighted the anterior and posterior cruciate ligament. They are a cruciform. They cross at the knee, and they prevent translation of the tibia primarily. So even if you look, if you were to grab the tibia there, if you were to grab the tibia there in the left picture and try to pull it towards you, try to pull it anteriorly, you would see that the ACL, by connecting to the lateral surface of the femoral condyle, it would prevent that forward translation. It also prevents that medial rotation of the tibia, which is why when we get to injuries, when we'll talk about this when we get to strain later, all of a sudden the fact that it has to carry both of those duties becomes a big deal. So one of the questions I was tasked to ask is, all right, if the ACL is particularly vulnerable to injury, then does the squat, does the jerk, does any of the movements we do or coach our lifters to do place the ACL under significant load? Let's do a brief refresher on mechanics. Boy, I'm terrible with this thing. So a brief refresher on mechanics. Sully talked about this a little bit in terms of how these tissues work as viscoelastic tissues. So when we talk about stress, we are talking about force over area. You see it on the left axis here. Anytime you increase the force on the tissue along its axis, if you look at a cylinder of steel like you have on the bottom right there, you have the increase of force. The wider the surface area, the cross-sectional area of that tissue, the lower the stress on that individual tissue. That seems relatively obvious. It's the same concept for when we contract muscle. Strain has no dimensions because strain is dependent on the length of the tissue itself. So you see here again on that steel cylinder there on the bottom right, your strain is the change in length of the tissue as it becomes under stress, divided by the length of the tissue itself. What we find is that mostly when you're dealing with tears, when you're dealing with ruptures, when you're dealing with major injuries to connective tissue, it is because strain becomes farther than the tissue can accept. It is literally stretched beyond its physical boundary. Now, our connective tissues are designed to enable movement while still allowing this because, after all, it has to strain in order for us to move. If you have a purely elastic tendon, then any stress on it whatsoever provides no force. If we take a perfectly elastic substance, as soon as we contract it on the tendon, there would be no movement, you would just have separation. You would be Gumby. Vice versa, if you were entirely viscous, if you resisted all forces going into the tendon, then you would structure, or you would place the bone to which the tendon is connected to under more force than it can really tolerate. We see that with arthroplasty, which we'll go into later, on the fact that the connective tissue, which is now the structure, becomes stronger than the bone, then the bone becomes a failure component. When we talk about stiffness, it's its resistance to deformation. The higher stress resists further strain. So immediately we think, okay, stiffness is a good thing. It's measured by Young's modulus. So when you look at this research, if you increase the stiffness of the tissue, we have increased its ability to transfer force and improved it without necessarily changing its size, which is something that comes important later. So our research questions, what forces do the connective tissues themselves see under load? And it gets really freaking complicated. So the only ways we actually have to measure force directly would be if you replace the joint itself. We did a total knee arthroplasty, a total hip arthroplasty, and we placed sensors inside that new joint to measure certain forces. We have actually done, but this has actually been done. And it provides some very useful information in terms of the force that is going to be seen by that instrument when you put it in a new body, but also what is happening to us while we lift. Even then, it's our best instrument, it's our best available data, it still has problems. Because in much of it, for instance, they're looking at these stresses and forces seen by people in the treatment phase, in the immediate 6 weeks after treatment. But people don't move the same way immediately following a total hip arthroplasty. That sounds kind of duh, but it's somewhat ignored sometimes in the literature when you see, oh, very low forces seen by walking, very high forces seen by different kinds of movement. It's like, well, yeah, they're still hurting. They're still in pain. 2 weeks ago, they had their entire hip replaced. How do you think they're moving? You can also see different, depending on how the arthroplasty is created. There's been numerous investigations, for instance, into changes of range of motion in the knee as it changes shape. And I'll leave this all to the material that Dr. Patrizio put together. But is the movement pattern the same between someone who's completed a complete arthroplasty, a total arthroplasty, and someone who has the initial healthy joint? Finally, it's easier to measure patellocompressive forces, patellofemoral compressive forces. It is a lot harder to measure moment. It is a lot harder to measure shear strain, depending on where we're looking, because oftentimes it's not like we replace those individual tissues that would be receiving that. The next way you can do it is by models, and this is how most of the research is done, and these models are useful, but like all models, they are flawed. If we take the 2D moment analysis that you see in Starting Strength, that you see in the books, that you kind of get, you have a comparative model. So I can tell looking 2D if someone puts their knee farther forward, if someone takes their knee farther back, what that does to the moment arm compared to each other. That doesn't necessarily work in 3 planes. So as soon as we change our stance width really wide, or as soon as any of that changes, that comparison between 2 movements is no longer coherent, can't be compared. Let's take that out in 3 dimensions. So we slightly complicated. Now we can accommodate a lot of changes there. But we still have levels of complication that completely messed with a lot of the original models before the 2000s. So when you're trying to create a model, not for the whole joint, but trying to figure out what is the ACLC, what is the PCLC, how much force do you have actually pressing in on the patella, you get issues of, all right, how much is each muscle contributing to this effort? So they strap on some EMG on somebody, have them, test out to a 1 rep max, or, the maximum voluntary contraction, and then use that as their base point. And while they're doing their leg extensions or whatever, they compare. So the EMG says they're at 70% of that, so there must be 70% of the force, usually using some conversion factor. Anyone who's read Sully's literature on EMG and Sully's kind of reviews of that, or even just thinks about it, knows that that invites error. We have the muscle length tension relationship. So we all know that the muscle does not contract at the same force depending on where it's at. Zhang et al., we'll talk about later, actually factored this in and found that a lot of the early studies exaggerated or overestimated the level of force on the patella in movements like leg extensions and squats because they weren't factoring that in. Connective tissue stiffness. We already talked about it. It's a variable that changes. Co-contraction. So my hamstrings and my quadriceps, they both operate against each other. I can have a net zero moment at the knee and have high patellofemoral compression forces because those two are acting against each other, especially the quad, operating over the patella as it contracts, as it extends, pulling that force down. If that PF compressive force is the issue possibly in a breakage, then we need to know, but it gets complicated. Also, because the models themselves are different, it gets very difficult to compare across studies, and in fact, I'm not really going to do it. Instead, comparing within studies, within similar models to get a general picture for what's happening. So just to give an example of how complex this can get, Zhang et al. In 1998, they did the leg press, squat, and leg extension. They came up with some useful pictures, or some useful clarifications to the models that were being done. But the biggest issues that are the biggest things that they point out that were validated later by future studies, the ACL not being highly strained in the back squat or the leg press. In fact, when he factored in the co-contraction of the hamstrings and when he factored in muscle length, or the muscle length tension relationship, the ACL in that model was almost completely neutral in terms of the stress on that tissue. Sounds very similar to something we are all familiar with in terms of the ACL. Patellofemoral compression forces were lower than previously described in all 3. So oftentimes when we're looking at, there are studies that are published that show, squats putting the knee under incredible tension, 12, 13 times body weight, but kind of have to look back at that, we're looking at material from the early 90s, the mid 90s. If those models did not factor this in, what are we looking at? Next, let's look at the highest quality data that we have. Instrumented arthroplasty. I have replaced this dude's joint. I have put sensors inside this dude's joint. What does it say? Just a quick summary, when you're talking about walking, especially walking downstairs, you end up with about 2.5 to 2.8 times body weight femoral compressive force. When we're looking at body tissues, when we're looking at the actual ability of the joint to actually sustain that, that is not an issue, that's not a problem, but it serves as a base point for later as we're considering possible long-term damage and load. Now, Bergman et al. Was a very interesting one because they had two subjects. It's an N=2 study, purely observation. They replaced one hip bilaterally, so both joints, and then one a single side total arthroplasty. So the highest forces that they observed were actually during stumbling, strangely enough. So they gave them a moderate pace running test, and they were getting about 6 times body weight, 6.5 times body weight. When the patients had to catch themselves, is when you saw the highest forces at 7.2 times body weight and 8.1 times body weight. So let's just throw the number 8. 2.5 for walking-ish, 8-ish when catching yourself from stumbling. And then Bergman, round 2, he did a future comparative study, taking multiple subjects using very similar models, instruments hips using accelerometers to measure contact force and torsion when walking downstairs instead of using running models, and we get about the same at 2.6. Our modeled estimates, strangely, and this is something I'll get to here in a second, get very similar data. Walking, we get about 2.5 times body weight. Running at 5.2 at a moderate pace. And then alpine skiing up to 7.8 times body weight. So when we look at the data, people talk about, oh, well, of course, these high-impact sports, these are risky to joints that are inflamed. They are risky to weak or damaged tendon. They are risky to rehabbing tendon or to replaced joints. But when you actually look at the data and you see the activities of daily living creep up into 8 times body weight, along with high-intensity sports like alpine skiing, and I mean high intensity because of the loading at the tissue, it sets it in perspective. Flynn et al. Was an interesting study. So the concept, this is kind of a PT concept. Let's take an exercise that allows us to train the tissue, but will minimize the strain done to the tissue in question. So how much contraction can we get without actually loading connective tissue? To us, that's kind of a strange question. Why would you not want to load connective tissue that adapts and evolves? But he tried backwards running, and we got some interesting data, 4.3 to 6.9 times body weight compressive forces, except he readily admits, he goes, but I just let them run as fast as they want. So they got to run as fast as they want over the force plate forward, and they got to run as fast as they want backwards, and admittedly, they were probably running a lot slower. So when you look at somebody who sets the speed evenly, who sets the speed and requires a forced pace on a treadmill, that was Scott and Winter, they got up to 11 times body weight on a sprint and 7.1 times body weight on a backwards run. So again, keeping those in perspective. Let's talk about powerlifters, because powerlifters are really where the research is about the things that we do. Schoenfeld has a great review on it, but in terms of the exact question I'm asking here, he cites Escamilla 2001, which has a couple of interesting conclusions. One, the ACL doesn't come anywhere near its limits in any of the models that have been tested, although he points out that in much of the research done, the lobar position, and any time you have a more forward inclination of the back, you decrease ACL stress. Duh. To us, this is relatively common sense. Back in 2001, there's a lot of question about whether or not the squat is itself dangerous to the knee. Now, the PCL is loaded, because if you looked at the two back in that cruciform picture, any stress, if there is no stress on the ACL, then the PCL is taking that load. One of the things he points out, though, is that the PCL is the larger of the two tissues, and we can talk about its break stress, its rupture strain, but is far higher than any of the forces measured for any of the movements. There was only one observed, metered incidence of a patellar tendon rupture in the research that he can find. Lifter doing a clean and jerk with 2 times body weight. It was a little over 2 times body weight. And they calculated 17.5 times body weight force on the patellar tendon, and it ruptured. In fact, if we get to a limit strength of 10 to 15 kilonewtons in a healthy patellar tendon, not really a problem for us. Briefly go through here and say why. So the highest, I'm only going to point to the highest values that were observed in all the research he was able to find on the squat. It's usually, there were a couple in here. When I looked at it, I didn't find where the squat was. There were knee extensions, but most of these are on the squat. The highest mean load lifted in this research was 1,982 newtons. For those not familiar with commie math, you have about 4.4 newtons per pound. So you end up with about 445 pounds being lifted, or in this case, about a little over 2 times body weight. The mean peak tibio-femoral compressive force at the highest angle they observed, which was 110 degrees for that study, you had less than 8,000 kilonewtons. So, 8,000 newtons. So when you are looking at the rupture force of the patellar tendon and what's seen by the ACL, not really a problem. Let's talk tissue adaptation, because that's the fun part. It's really an optimization strategy. We don't want it to be too loose. We also don't want it to be too stiff. And it can actually become too stiff in certain pathologies. You basically have 2 options then. Does the tissue actually hypertrophy, or does it change in stiffness through some other mechanism? We'll look at Bohm et al. As probably the biggest and most consistent study of this. It is a meta-analysis and systemic review. In general, tendon does not get bigger. It does a little bit. And when he looked at some of the research, they're limited by the usual 3-month, issues, and there was still development. So he admits it's possible that it does grow bigger, but not by much. Mostly you're looking at changes in the extracellular matrix. You're looking at improved cross-linking in the tissue that improves stiffness. Here's something fun. Across all the studies that they evaluated, if you pulled it out by intensity, so 70% or higher compared to 40% or lower, 50% or lower, the high intensities had a moderate to high effect size for increased tendon stiffness. The lower intensities had 0 effect size for increased tendon stiffness. It was like 0.2, like 0.02, sorry. Short duration of improvement because the studies were short. The interesting thing is plyometric training was ambiguous. So we think, there's kind of the magical thinking, well, if I strain the tendon in such a way as it is required to strain, goes through its viscoelastic cycle more powerfully, it will adapt better. But in fact, all of the work done in plyometric training was ambiguous at best, and only one of the studies even showed significance. We do know that age and disuse reduce tendon stiffness, period. End of story, it just happens. As we get older and as we disuse, one thing that keeps coming up again and again, disuse is its own injury. Immobility is injury in connective tissue. Creep, repeated load at high intensity causes creep. Creep is what happens when you subject a tendon to a certain load, a certain stress, and it strains a certain amount. You subject it again to that stress. You subject it again to that stress. The 4th time it goes a little bit farther. You subject it again, it goes a little bit farther. It starts to creep at the same level of force, and all of a sudden, you're not dealing with a tissue that has the same properties. You're dealing with one that will reach its limit faster, which comes up in research later. Reeves is super cool. I wish I could say that this was a great study. Unfortunately, it's only done on 9 septuagenarians. They did sets of 10 at 80% of 5 RM on the leg extension 3 times weekly. Is it a perfect study? No. But one of the things that they found was improved tendon stiffness, rate of force development, and strength dramatically increased. It was significant. Looking at the data, looking at the percentage improvement, I'm like, that would be what I would expect to see from someone doing consistent training 3 times a week for 14 weeks, no changes in controls, and an increased stiffness to the point some of them were actually doing pretty normal for younger cohorts with no noticeable hypertrophy. When it comes to tendon, the research isn't good enough to discuss optimization. It's just not. You have to go heavy. You have to stay heavy relative to what you're capable of at any age, and you have to train consistently. So cartilage. Kind of blow through this one because the answer is it really doesn't adapt to load. So Eckstein et al. Is the best review on this. It's called Exercise and Articular Cartilage. Cartilage thins under extensive periods of unloading. It's like this theme comes up. Sedentary lifestyle and immobility is a problem for connective tissue, just period. Cartilage thickness varies regardless of athleticism. If I take the most sedentary couch bum and the best athletes here and take a random sampling of your cartilage thickness, probably no correlation or a very small one. And if anything, it's probably a reverse correlation. Those who are born with thicker cartilage are at least not experiencing unloading issues and are able to sustain that level of intensity. Age, sex, and disease conditions affect cartilage deformation, not training status. Twin studies suggest there's a lot of genetics involved. So it's unfortunately one of those things where you're kind of stuck with what you're stuck with when it comes to cartilage, except that you can make it worse. Brahmer et al., it's a really ugly study. And it's done on horses specifically, so they make a lot of claims about, hey, this is justification for training while the cartilage is still maturing because it encourages greater size. But there are enough limitations on this study, I can't buy it. Rusin showed improved proteoglycan content after 4 months of exercise. I want to believe it, but it's a case of biomarkers only, not a lot of straight data, and there was no measure of any actual, useful straight metric. This is fascinating. Okay, finally, Azukizawa. The most useful part here is that 12 weeks of strength training, it was a straight biomarkers measurement. There's only so far you can go with it, but it didn't harm those with osteoarthritis, which is a big key. When people say, hey, I have arthritis, can I train? Repeatedly, we see in the literature again and again and again, yes, you can train. Conclusions for cartilage: even moderate activity. Doing something at least doesn't damage cartilage. Don't expect it to repair or get better through strength training, and it does not appear to damage cartilage even under the highest loads we can sustain it to.